In our previous lesson, we discovered that electric charge is a fundamental property of matter. We learned that like charges repel, unlike charges attract, and objects become charged by gaining or losing electrons. But one important question still remains. We know these two charges repel each other. But how strongly do they repel? Is the force always the same? Or does it depend on something else? Now let's look at a positive charge and a negative charge. They attract one another. But here's the interesting part. How strong is that attraction? Imagine we slowly move these charges farther apart. What do you think will happen? Will the force stay the same? Will it become weaker? Or perhaps disappear completely? Let's try something different. Instead of changing the distance, suppose we increase the amount of charge. What happens now? Does the force double, triple, or does it behave in a completely different way? These are not simple questions. For centuries, scientists knew that charged objects attract and repel, but no one knew exactly how much force acted between them. Could there be a mathematical law that predicts the force between any two charges? Nature is full of patterns. Apples always fall toward the earth. Planets move in predictable orbits. Magnets attract iron. Scientists believe that these patterns are not random. They are governed by laws. So here's our question. Does the force between electric charges also follow a pattern? Let's investigate one variable at a time. First, we'll keep the distance between the charges fixed. Now imagine increasing the amount of charge. As the charges become larger, the force between them also becomes stronger. This tells us something important. Greater charge produces a greater electric force. Now let's keep the charge the same. Instead, we'll change the distance between them. As the charges move farther apart, the force between them becomes weaker. The farther the separation, the weaker the interaction. From our observations, we've already learned two important facts. First, increasing the amount of charge increases the electric force. This tells us that the electric force is directly proportional to the charge. Mathematically, we write F is proportional to Q. But as there are two charged objects, if increasing the first charge increases the force, then increasing the second charge should also increase the force. Therefore, the force is directly proportional to product of both charges. Now the second fact is, increasing the distance decreases the force. As the charges move farther apart, the force becomes weaker. But here's the interesting part. The decrease is not proportional to the distance itself. It is inversely proportional to the square of the distance. If the distance doubles, the force becomes 1/4. If the distance triples, the force becomes 1/9. We now have two separate relationships. The force is directly proportional to the product of the charges and inversely proportional to the square of the distance. Combining both, we obtain this equation. This equation tells us the relationship of force with charges and distance between the charges. But it is still incomplete. To convert a proportionality into an equality, we introduce a constant of proportionality. This constant is represented by the letter K. And now, we have reached one of the most important equations in electrostatics, Coulomb's law. It states that the magnitude of the electric force between 2-point charges is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. Notice something. This equation wasn't something we memorized. We built it from simple observations. We have successfully discovered Coulomb's law, but before we use it, we need to understand what every symbol means. Think of this equation as a machine. If we know what goes into the machine, then we can figure out what will come out of it. Most important is to know the units of every physical quantity associated with every symbol, because it is where most students do a mistake. Think of it as like you want to measure the amount of milk. Then it can be measured in liters, and if you want to measure the distance of your school from your home, then you can use kilometers. But amount of milk cannot be measured in kilometers, or distance cannot be measured in liters. Similarly, it's very important to know the measuring unit of all the stuff in Coulomb's equation. The first symbol is F. It represents the electric force between two charged particles. Remember, force is always an interaction between two objects. If the charges repel, the force pushes them apart. If they attract, the force pulls them together. If we look at its SI units, then force is measured in newtons, abbreviated as N. The symbols Q1 and Q2 represent the electric charges on the two particles. These charges can be positive or negative. Their SI unit is the Coulomb, represented by the letter C. The greater the magnitude of the charges, the stronger the interaction between them. The symbol R represents the distance between the centers of the two charges. This distance is extremely important. Even a small increase in separation can reduce the electric force significantly. In SI units, distance is measured in meters, represented by m. Notice something unusual. Distance doesn't appear by itself. It appears as r squared. That means the force decreases much faster than the distance increases. That is why it is called as an inverse square relationship. Now let's understand the only new symbol in the equation. K is called Coulomb's constant. Its value in air or vacuum is approximately 9 times 10 to the power 9. This constant sets the scale of the electric force. Without it, the equation would only tell us how the force changes. With it, we can calculate the actual force. Let's read the equation one final time. The electric force between 2 point charges equals Coulomb's constant multiplied by the product of the two charges divided by the square of the distance between them. Every symbol has a clear physical meaning. Once you understand that meaning, the equation becomes much easier to remember. We now understand every part of Coulomb's law. The next step is to use it. In the next segment, we will solve numerical problems step by step and see how this equation works in practice. Thank you for watching. We will meet in next lesson.